About Chebyshev's theorem. And Chebyshev was a Russian mathematician. He did a lot of work with statistics too that we use. And he was the one that came up with this rule. Well, at least he's the one that has been given credit for coming up with it. And it says that for any data set, and as you'll see in a couple of weeks, in 2-3 weeks, we're going to look at the normal distribution, and there's a special situation for that, which goes with Chebyshev. He says if you go 2 standard deviations either side of the mean, so this symbol is the mean, and since some of you asked about symbols, take these notes because you're going to see these symbols often. Mu is the population mean, and x bar is the sample mean. Okay, here we're just talking about population mean. And this little fancy 0 or O with a line over it, that's sigma. That is a lowercase sigma, Greek alphabet sigma. So is mu is the Greek alphabet too. And that's the population standard deviation. Okay, S is used to denote the sample standard deviation. This is the one you've been calculating when you do n-1 divided by n-1. Population standard deviation. Similar, it's a little bit different calculation. I wouldn't worry about it. Just know that that's what the symbol means. Okay, so that's what those mean. So then they gave us this, so this is on page 101 of the 3rd edition. So they gave me this data about number of violent tornadoes in the U.S. for each year. So these are the tornadoes per year. And they're telling us to use Chebyshev's theorem to give an estimate of about 75% of the years will have how many tornadoes. I copied the data into a spreadsheet, and I let the spreadsheet calculate the mean and the standard deviation. Okay, and then I'm looking at Chebyshev's theorem. It says if I go 2 standard deviations either side of the mean. So what I did is I took the 46. I guess I should say I doubled that because it's 2 standard deviations. Then I subtracted that number from 46.2 whatever, and then to get the upper bound, so that's the lower estimate, and the upper estimate, I had doubled this standard deviation and added it to that, and that's the upper. So 75% of the years will have between just under 2 to just over 90 violent storms per year. And then for the next part down on that page, or maybe on the next page, it says, yeah, I've come up with the 88.9% estimate. So I did 3 standard deviations either side of the mean. So I went back and I instead of multiplying by 2, I multiplied this by 3. And then I added it and subtracted it. Notice now I'm getting a negative. I can't have a negative number of storms. So really it should be using 0. That doesn't include the full range, but I mean, we got to make sense of the data too. So I could have 88.9% of the years at the time will have up to almost 113 violent storms. And then for the 98.3% of the time, we did 4 standard deviations. So again, how did I do this? That's right, I multiplied this times 4, subtracted it to get the lower bound, added to get the upper bound. Again, I get a negative number. Okay, so up to as many as 135 violent storms per year. Then I asked myself, so this does work for any distribution. I wonder what the shape of this distribution looks like. I used that Rossmann chance applet that I've linked to, and I had it create a dot plot for me, and that looks pretty right skewed. And then it would let me add a box plot in here. And what's really nice about this applet is that it automatically calculates the outliers. It uses some rule, which actually you know the rule, that to calculate. So it shows these are outliers. So these numbers are outliers. And see, there's 2 of them, and they kind of look like outliers. So what's the shape of this distribution? It's right skewed. The median is somewhere around 40, just over 40. You can kind of see that from the box plot. Since it is a skewed distribution, we probably shouldn't be using the mean and the standard deviation to describe it. We should be using the median and the 5-number summary. That's not where this section in the book was going. They wanted to use Chebyshev's theorem, but really, this is what we should be doing. So I went and ran with this a little bit. So I let the spreadsheet calculate the median and the 5-number summary. Something that you might run across is that Excel is calculating the standard deviation, the quartiles a little bit different than, say, a graphing calculator will. And there's a couple of different ways to do this. I used to really be upset about this. Now I'm just saying, it's still about a quarter. That's about a quarter. That's about 3/4. Does it really matter that it's a slightly different number? We're trying to get a picture of the distribution, come up with the estimate. So when I do it by hand, I use the same way the calculator does. Excel and Google Sheets does it slightly different. So, anyways, one way to figure an outlier, and you've read this in the textbook, is that to use the interquartile range, and then you take 1.5 interquartile ranges and add it and subtract it. So I took Q1 and I subtracted 1.5 times the IQR. So to get this lower fence, this negative 6.5, I took 31 minus 1.5 times 25, because that's the interquartile range. Remember, interquartile range is this difference between the upper quartile and the lower quartile. And that's where I got that lower fence. And then to get the upper fence, I took Q3, which is 56, and I added the 1.5 times the 25. And that's where I came up with the 93.5. And then I sorted the data, and look at that. Anything bigger than 93.5 is an outlier, and there's those 3 points, and that's what we saw with that dot plot. You remember there was, let's see, let me find it. So you see that they had the applet broke out those two, and we are only seeing one dot here because there's 2 data points that are exactly the same. So that showed those outliers, and that's how it came up with it. So